Okay, welcome to the third video in the data section. It's about histograms and percentiles. This is, to a large degree, many of you will have covered this ground in GCSE, but so it's a little bit of a kind of a reprise of that. But it allows us to set the context for some of the things that are going to go later. So here we go. Let's have a look at this situation here. This is a this is a bit of a survey that's been done. 100 cars, and well, I don't know. We've stood on some road somewhere and actually measured their speed and kept a record. So we've got 100 readings, but then what? In order to 100 separate readings is a little bit difficult to digest and to make sense of. So what we do is we categorize the data, and what we've done here, we've categorized it into bands. Speed, this is all in meters per second, between 20 and 40, 40 and 50, 50 and 55, 55, 60, 60 and 70. And we've got the count of the number of cars going at that speed for each of those categories. This conveniently adds up to 100. But what we do notice is that these intervals are not all the same width. This is 20, this is 10, this is 5, and so on. So we go class width. Okay. So what the way we present this on a frequency density chart, and that's what we've got here, is for each class interval here, what we do is we make this area proportional to the frequency. So there are 5 in this bottom category here, 20 to 40. So that's 5 out of 100, or 5%. So the total area of this shape here, if we can imagine this whole shape here, so 5% of it is this area here. So it's the area that represents the frequency. Usually have to find your own scale and your own conversion factor. All we're saying is that it's 5% of the total, 0.05 of the total. So there we go. So that's what we have done here. We call these kind of diagrams frequency density diagrams because we are interested in the areas. Do note though that if the frequency of the class divisions are all equal, then effectively it's proportional to the height. So the height, because the height is the area is proportional to the height, so the frequency therefore is proportional to the height, and we tend to call those frequency mass diagrams. So it's a little bit of a kind of an arcane distinction in a way, but if you come across those two bits of terminology, mass and density, it's for that reason. But as I say, if the class intervals are the same width, then it's the same thing really. Okay, so so that's what we've done. We've charted that. I mean, the diagram itself does not necessarily help us to draw many conclusions. So what, for this kind of purpose, what we find most useful is to have is to do the cumulative frequency. So we've got the same thing here. I've stretched out the scale a little bit, and this area, we just represented it here. That's 5%. But we could say, if we think about this differently, we could say, well, between 20 and 50, we've got 20. Okay, so this box here represents that fact. Let's kind of group the bottom two categories together, and we've drawn the box that we would have had on here. as we've done that, and then we just carried on that process there with the 20 to 55. That's this one. 20 to 60, that one, and then 20 to 70. That's captured all our frequency into that. So the boxes themselves kind of don't tell us too much, but what we do, if we draw in this line which connects the corners up like this, then this gives us a rather useful curve. It's not really a curve because it's made of straight lines, isn't it? But we could actually draw this. We could turn this into a curve. We can actually, if we're good at drawing, we could actually make it look more like a curve. Like that sort of. It's got that sort of S shape in it, hasn't it? We could do that. Personally, I'm not very good at drawing curves, and it's equally acceptable to do it either way in most circumstances, unless you're told in the question otherwise. But what this does mean is that here we go. We've got the class intervals here, and going up here, we've got the percentiles. Okay, so this one, well, we know this is 5% here, so this would be this here corresponding. If we drew this along here, we'd actually get to 5%. See, these are all percentages. If we multiply them by 10, so 5% will be here. Okay, and then of course these first two are actually 20. That's 20%. So that's this point here. Okay, so as we go up, we've basically got more and more of it in there. Well, we talk about, so this is the 50th percentile here. So at this point here, 50, what is it? What would be 55, something like that. Just a bit over 55, 56 maybe. It's that blue line there. What we're saying is that 50% of our sample is below 56 miles per hour, and 56%, and then all this area here corresponds to here above 56 miles per hour. So what we're saying is the 50th percentile represents the point at which we estimate. Now, let me just say at this point that we've thrown all our original data away once we put them into these categorizations. So what we're now having to do is to kind of try and estimate back the original data that we had. I mean, it's completely normal and typical situation, but that's what we're doing. So we're sort of saying that, well, we're estimating that over 50% of our cars are traveling at less than 56 miles per hour, and 50% of our cars traveling at more than 56 miles an hour. So that's the median. We've got the 50th. This is called the 50th percentile here. So this 56 is the 50th percentile, and the 50th percentile is what we call the median. It's the middle. It's the middle of a whole set of numbers. And it may well be that if we were to go back to the original data and order all these speeds, that if we go to the middle, it would indeed be 56. But having kind of thrown our original set of data away, if we can imagine it that way, then it might be 57, it might be 55, but 56 is, for the purposes that we want for doing these things, 56 is just fine. So we're saying from this diagram that we estimate that the median, the 50th percentile, is 56. And we can also look at the other percentiles as well, the 10th percentile or the 90th percentile or whatever. Most commonly what we do is we look at the quartiles. So the lower quartile would be 25%. Here it looks like about 51, doesn't it? So we would say that 25% of the cars are traveling at speed which is lower than 51 meters per second it is. Okay, and therefore 75%, which is the kind of this lot up here, are traveling faster than 51 miles per hour. And then 75%, that's the 75th percentile. Here we go, 75% along this scale here. And that corresponds to this value here, which looks like about 59. So again, we would say that that 75% of the cars are traveling at less than 59 meters per second. And 25%, that's the remainder, are traveling faster than 59 meters per second. We're kind of assuming that you know, these are you know, it's going to be some decimal value, and that the probability of traveling exactly at a certain speed is kind of infinitesimally small. But so that's the premise on which we're building that. So that is that. So that's the cumulative frequency chart. And generally, for representing this kind of data, I mean, this is where it becomes useful, because we want to draw conclusions about medians and percentiles, because that then gives us our measure of central tendency. A median is a measure of central tendency, along with mean, by the way. Mean is another measure of central tendency, but we're interested here in the median, and also gives us an idea about the spread. And very often we're trying to be interested in the, you know, how wide this interquartile gap is. The interquartile gap is the gap between the quartiles, and the quartiles are 25% and 75%. So this difference between 59 here and 51, that's 8, isn't it? So that would be the interquartile range, and that gives us quite a good measure of the data. So we're looking at those two as being the principal measures. You know, the median and the interquartile range tend to be things that we're mostly interested in. Okay, so that's the kind of the basic thing. Let's have a look at one or two examples. The runs scored by a cricketer in 11 innings during the 2006 season were as follows. A list of numbers there. The exact value of A was unknown, but it was greater than 100. Okay, so these are in no particular order. Calculate the median and the interquartile range of these 11 values. Okay, so what we need to do in order to do this is to actually put them in order. I mean, we could draw our chart as we did above, but we've only got 11 numbers here, so we're actually quite comfortable handling 11 numbers. It's, you know, we're only going to categorize them if there are a lot of numbers. So there we go. So I put them in order: 0, 0, 13, 28, 35, 40, 47, 51, 63, 77, and A, we know this is A is greater than 100, so that must be the top one. And the median is the middle one. Okay, that's, in this case, it is this 40 here. Now, you may well say, well, what happens if there's an even number? What do we do? Well, we would then take our median as being the mean of the two either side. So if there were 20, for instance, there would be the 10th and the 11th, and we take the mean of those two, and the median would be the value in the middle. It seems like the fairest thing to do, doesn't it? Okay, so, and the interquartile range, well, we more or less got to do that here in this situation, because having taken the middle here, then our quartile is going to, you know, that will be too low, that will be too high. This one, it's going to be this in between. So there we have to take the mean of these two numbers, which will be 20.5, and correspondingly up here, the upper quartile here we'd be taking the mean of these two things, which is 57. So so the median is going to be 40 for this data, for these data, if you like. And the interquartile range would be the difference between 57 and 20.5, which would be 36.5. So that would be the interquartile range. Give a reason why for these values. The mode is not an appropriate measure of average. Yeah, mode is the other average after mean and median. It's not at all useful, is it? I mean, we've got 2 zeros there. It would be that. It's not telling us anything at all. It just happens to be the value that crops up twice. So not at all appropriate. The range is not an appropriate measure of spread. Well, the range would be is the whole range from from one end to the other. Well, why is it not appropriate? Well, first of all, we don't know what this top one is, so we can't even calculate it. So it's certainly not appropriate if we can't calculate it. But the other thing is that we tend not to be too interested in the range, the entire range of a set of numbers, simply because we tend to find that the numbers outside the quartiles are often not really too representative of the data. There's certain reasons why they might be very low or very high. Sometimes we call these outliers. You'll have heard that term, I reckon. An outlier is something which is just that there's some other factor that comes into play, which means that it's not actually terribly representative. So we're usually interested in the interquartile range as being a good measure of the spread. But sometimes we want the range of the whole thing. Again, it depends on the question. Okay, so let's just have a look now. This is one. Coffee is sold in packets. A seller measures the masses of the contents of a random sample of 90. Well, we wonder how it was randomly selected. I want to go back to our sampling methods there. Anyway, it's random as far as we're concerned. Packets of coffee from her stock. The results are shown in the table below. So this is very similar to what we've, what we had further up. Got these bands here. And again, that's 5 wide, that's 3 wide, that's 4 wide, and so on. So not actually the same widths, are they? So very often we're interested if we take the midpoint. Actually, it's useful to take the midpoint when we've got a band like this, and then the frequency. So that's the number of packs that are in this category here. So again, we've categorized it. We can't deal with. There's too much data here. There's 90. We couldn't deal with it unless it was categorized like this. Okay, so that's what we've got. Now sometimes we look at this data and say, well, let's kind of work. Well, let's work back. If we wanted to find out the mean, for instance, well, of course, if you had got your original 90, you'd add them up, divide by 90, that would be a mean. But we can still get a good estimate of the mean just by using this table, and that's always really always relevant. And we do that by, well, we're sort of assuming that these 8 are sort of kind of evenly spread amongst this group here, so there's as many near to 240 as there are to 245, and so on. It's basically just evenly distributed, and so therefore we could get an estimate for the total mass of these 8 in this band simply by multiplying the midpoint by the frequency. And if we did that for each band, we'd have an estimate for the total mass in each band. And therefore, then if we added all those up, we would have an estimate for the total mass of all 90. And then if we divided that by 90, we would have an estimate of the mean. So that's something that that does crop up. Okay, so but we're not looking at that just at the moment. But incidentally, I've left this in here. This is not relevant to this what we're using this question for at the moment. We're actually going to come back at some stage to this question, and they're giving us this thing here. Fy squared equals this huge number. Now this comes in relevant when we're actually trying to measure spread. Not got there yet in this in this video, but this, what would this mean? So this is what we're doing with this is we're taking, see, midpoint says midpoint y. So what we're doing is we're squaring all these numbers. This is why we've got something quite big. Squaring 242.5, you get quite a big number. So we square that and then multiply by the frequency and do that for each of these rows, and then add them all up, and that's what the sigma sign means. Add them all up, and that would be this. Now we're not going to use this now, as I say, but we will be interested in this later on. So it's just something to note and hold that thought, as they say. Use linear interpolation to estimate the median mass of the contents of a packet of coffee to 1 decimal place. Cool. Right, okay, well, I've drawn the frequency density here. I've done all that. Right, so, and we've also drawn the cumulative frequency here. Okay, so that's done in exactly the same way we did it above. We've just taken this box represents the first category. This box represents the first 2 categories banged together, added up, and so on, 3, 4, 5. And we've drawn our curve, which usually, not always, but usually has a sort of a bit of a kind of an S shape to it. You might want to just ponder why that is. But and again, we'll come back to that. So we're trying to estimate the median. So well, the median is the 50th percentile. Okay, so we're coming across from the 50th percentile. I'm just trying to remember where I actually drew it. 20, 30, 40, 50. It probably should be a little bit further up, but anyway, so if we just follow that across from the 50th through to the line and back down, it gives us the measure here at the bottom. I've concluded it's 250.6. Can't really tell from the diagram, but that's how we've got that number from going through that process. I'm looking at it again, it might be a bit higher, but that is basically what we're estimating the median to be. Okay, so that is that. And I think well, we'll just have one look at this one more example here. Rihanna wishes to catch a train from her local station to the city centre. There are 2 local taxi companies, Blue Star and Green Star. In the past, Rihanna has telephoned both companies. At the time in minutes that she has to wait between telephoning and the arrival of a taxi are summarised in the box and whisker plot. Now, box plots, here they're called box and whisker plots, but I can just call them box plots. Basically, what we have to look again against this scale here at the bottom, and what this is saying for Blue Star is that the quickest is like no minutes. might be 1, but somewhere very small anyway. And the highest is what this is, where we follow this down, it'd be about 33 minutes, wouldn't it? So you might have had to wait 33 minutes. But out of all the times, the median time, so if you wrote all these times down, the middle one would be here. And that looks like about 18 minutes there. And then we've got percentiles as well. So this part of the box here represents the lower percentile, that's 12 minutes. So that's saying that that 25% of the taxi occasions, the taxi arrives in less than 12 minutes. Okay. And then here we've got the upper quartile at 23 minutes, and that's saying that 75% are less than 23 minutes, and correspondingly 25% are more than 23 minutes. Okay, so that's what that means. And we got the similar thing here for Green Star. Now if we do a comparison against our cumulative frequency, we see that, you know, this corresponds to this, this corresponds to this is the median here, that's the upper quartile, and this is the top end of the range, and exactly aligned up, but that's the basic idea. So it kind of, what it does is it represents this, but it does it in a rather more succinct way, I suppose. You know, if what we're interested in, as I mentioned before, is really the median and the interquartile range, then this box plot kind of does it really. Okay, so so we got the same thing for Green Star here. Compare briefly the waiting times for the two taxi companies. Well, this comes back to what I've just said, really, is that the two things that we're interested in are the median and the spread. And when we talk about spread, usually more kind of reliable to talk about the interquartile range, unless we are told otherwise. So what we're saying here is that in comparing these two, well, Blue Star has a higher median, and Green Star has a lower interquartile range, the range being a single number, being the difference between that 18 and that 12, 11 there. Okay. So, to be honest, it's a bit of a no-brainer, really, as to which taxi company you would you'd kind of go for here, because Green Star kind of wins on both counts. But very often you'll see these where the one with the lower median has got a bigger range. So then you have to think, well, what we're interested in, is it the sort of predictability of the arrival of the taxi, or is it the you know, the median? That might come into play. Giving a reason for choice, I advised Rihanna on which company to telephone if in order to catch the next train. She needs the taxi to arrive within 5 minutes and 25 minutes. Okay, so well, yeah, I think basically we'll be going for Green Star here, wouldn't we? I mean, it's kind of got its 75th percentile down at 18 minutes, whereas this one's up at here. But what we don't know is we don't necessarily know how these whiskers here are spread. But I think on the evidence of, you know, just the box plots, I think we'd have to go for Green Star. But it could be that if we saw this full thing here, you know, and it was broken down differently, maybe into we could see it in terms of 10 percentiles, you know. So instead of four strands to our data here, we might have 10. We might well actually conclude that Blue Star is more reliable. Certainly, if Green Star's got a high proportion up at the top end here, then you know, we might be a bit nervous about getting it. So we don't know. We're assuming these are all kind of evenly spread along here. All that 25% of them on that, all that 25%. And if they are evenly spread, that's one thing, but they might not be. Okay, so that is all I think I wanted to say at the moment on this topic. We'll be going on to talk about measuring means and spread in kind of in slightly more sophisticated ways in the next video. So I will see you then.